This is the first video on Chapter 30, Rates of Change. And what I'm going to do is I'm going to explain why the derivative of a function is the instantaneous rate of change. And it's a similar logic to why the derivative is the slope of the tangent line. So when the independent variable, that's what we usually call the x variable, so that's the thing you plug into the function. When that variable changes from c to x, then the dependent variable, that is, say, y equals f of x, so y is the dependent variable, that's the variable that depends on the function. That variable changes from f of c to f of x. So we start with c and its function value. C then changes to x. The function value now changes from f of c to f of x. The average rate of change is going to be the change in the y divided by the change in the x, or the change in the dependent variable divided by the change in the independent variable. So we have f of x minus f of c divided by x minus c. This is the average rate of change of f with respect to x. Now, we don't want the average rate of change, we want the instantaneous rate of change. So what do? We do a similar thing that we did for slope. We'll take better and better averages. So we'll look at what happens as x gets closer and closer to c, but isn't allowed to actually be equal to c, because then we would be dividing by 0. So what is our notation for that? It's the limit. So we take the limit as x approaches c of f of x minus f of c divided by x minus c. We take better and better averages. But then we look at this limit and we recognize it, and we say this is the definition of derivative of f at c. So the derivative of f at c gives us the slope of the tangent line at the point c f of c, but it also gives us the instantaneous rate of change of f at c.